Kato, Tokyo Institute of Technology, and also COE of his own company for this third of this Drapier lectures. And I think yesterday Kato presented periodic numbers to high school students. It's rather a difficult task, and I believe he succeeded. And the day before yesterday, his talk was even more challenging and adventurous. I believe today's talk is his own field, so he's more kind of comfortable. And it's about non-archimedean geometry. Actually, to study mirror symmetry, I need to learn something about non-archimedean geometry. So I try to learn something from him. And he wrote some very big book on this subject with his colleague, Fujiwara. And actually, he says that this is too difficult for you, so I didn't read it. But I hope today's talk of him is suitable for me. So please.
Okay, thank you for the introduction. So this is my third talk in the Della Pietra lecture series. And this is a talk for, this is a technical talk for faculties, postdocs, and graduate course students. And I chose this topic for this third talk. This is about non-Archimedean geometry, non-Archimedean analytic geometry more precisely. This is one of my major research fields. So let me start from the introduction. The first slide is about some keywords which we are going to use in our discussion later. So first of all, what is non-Archimedean geometry? So what it means is a certain analytic geometry over non-Archimedean valued field. Or here the geometry is analytic. This is one of the most important points because algebraic geometry can be always carried out for any field. But the point is that this is analytic geometry, which, for example, cannot be done, which is very hard to be done, for example, over a finite field. But if you have a valuation, then certainly you can do. So this is what we are going to talk about, discuss about. So, and this non-Archimedean geometry should be compared with the so to speak, complex analytic geometry, which all of you know, which is analytic geometry over the field of complex numbers, C, with the usual absolute value valuation, Archimedean valuation. The first idea of non-Archimedean geometry comes out the analyticity, which is defined via convergent power series. I mean, the analyticity means analyticity of functions, and analytic function in our context should be defined by means of, at least locally, should be defined by means of convergent power series. And the convergence and also the radius of convergence and so on, this kind of notion makes sense over any valued field, no matter whether non-Archimedean or Archimedean. So if you have valuation in your field, then you can certainly talk about the convergence and the radius of convergence, and also the analyticity, at least locally. And this, however, will cause a lot of problem as we see later in the slides. And I also would like to mention some unique history, the historical aspects of non-Archimedean geometry. There are actually several technical problems. ACP is analytic continuation problem, and the other one is FP, the functoriality problem. I'm going to explain these problems in later slides. But because of these technical problems, we have sort of mismatchings between the kind of fatal mismatchings between spaces and functions, which didn't appear in complex analytic geometry. But in the history, there was a big turning point when the so-called rigid geometry came out from the idea of John Tate in 1950s. And since then, we had a big progress in this context, and especially the last 50 years, we have several major breakthroughs. We are going to discuss about this as well. Okay, so let me start historically from the non-Archimedean function theory, because I mean this is the correct way. I mean, according to the historical point of view, the complex analytic geometry has also been developed from the notion of analytic function. So we should put non-Archimedean function theory as a first sort of starting point. Okay, so there is a let me just list up some historical event. So the history of non-Archimedean geometry or non-Archimedean function theory has begun when Kurt Hensel discovered periodic numbers in the end of 19th century. And so if you see, for example, in the third line, the notion of analytic functions have been already studied in early 20th century over non-Archimedean valued field, nicht archimedischen bewerteten Körpern. And already in the first half of 20th century, there was a big discussion about the analytic continuation in the non-Archimedean situation. So the discussion is about this. So here is the explanation, the first explanation of the problem, the analytic continuation problem, ACP. So let us consider the following situation. K is an algebraically closed, complete non-Archimedean valued field. Okay? And Fx is a formal power series having positive radius r of convergence. And you take any point A in the open disk of radius r, here the minus sign indicates it is open disk, centered at the origin. And you take the Taylor series as usual, centered at x is equal to a of the function f. And you will find, strangely enough, you will find that the disk of convergence of this new center is actually the same disk you start from. So in the complex analytic geometry, you have the new disk which some part sticks out from the original disk, right? And you take another point, and then the new disk sticks out, and in this way you can go on the continuation. This was the conventional sort of phenomenon. But what you have here is totally not like that. So I mean, even though you take another point, I mean, not on the not the origin, you have the same disk always. So this means that the analytic continuation, in the classical sense, can never work. So this causes a lot of problem, as you understand now. So why this kind of thing happen? So one of the reasons is what lies in the topology of the non-Archimedean metric space. So let me go back to the more basis, so to speak, the story about the non-Archimedean metric spaces. So, but before that, maybe I need to present the definition of the non-Archimedeanness in this context. So a metric D on a set X is non-Archimedean, maybe many of you know, if for 3 points x, y, z in X, the distance between X and Z is less than or equal to the maximum of the distance between X and Y, or distance between Y and Z. So this is the non-Archimedeanness sort of condition, which is in fact the stronger condition than the usual triangle condition, triangle inequality, as you know. Okay, so what do we have in this metric space? So first of all, if D is non-Archimedean like this, then first of all, any open ball is closed, and any closed ball is open. So all of them are clopin set, so to speak. So closed and at the same time open. So this is one strange property, and another one. So two balls intersect only if one contains the other. Okay, so there is no such non-trivial intersection where one of them sticks out from the other with no empty intersection. This doesn't happen in non-Archimedean setting. So this partly explains why we have that problem, the ACP, in the previous slides. Okay, so this kind of thing doesn't happen. Only these things happen. Okay, the third one, any point in a ball is the center of the ball. So there is no unique center. So every point in the ball is a center. So every person in a country is a king of that country. So this is a very kind of a utopia sort of thing. And the fourth point is even more strange. Usually people think that diameter is larger than radius. But in non-Archimedean situation, the diameter of the ball is actually at most the radius of the ball. So I mean, it of course depends on the definition of diameter, but I'm using a usual definition of diameter. It's a supremum of the distance of 2 points in the ball, right? So then diameter is not, for example, the twice radius. So in this setting, so diameter is at most radius. And finally, the property of a non-Archimedean metric space is that the metric topology is actually totally disconnected. And here is what it means by totally disconnected. A topological space X is totally disconnected if any subset consisting of at least 2 points is not connected. So there are too many non-connected subsets. Okay, so having these metric spaces, I mean, these metric spaces are metric spaces. They are Hausdorff and locally compact. So very, very nice. Maybe it seems very nice, you might think. But if you start from such a metric space, you have a lot of problems, lot of strangeness. And maybe the fatal problems, I give you 2 problems, especially in developing analytic theory over such space. So the problem number 1 is that the topology is too fine. So there are too many Klopen subsets. So I mean, most of the subsets are not connected. So, and this also means that there are too many open coverings. And having too many open covering causes a lot of problem in linking local property and global property. I mean, so in analysis, you should start from local theory and gradually go up to the global theory by gluing. So in this sense, you have to somehow keep linking between local and global. But this is something impossible in non-Archimedean geometry because there are too many, extremely many open coverings. So this is problem number 1. And the second problem is that, sorry, okay, there are too few points. For example, I mean, the set of rational numbers in the real line is totally disconnected. And things are a little bit similar to this. So imagine you have to develop analytic theory or differential calculus over the set of rational numbers. I think this is going to be a disaster. You have to add more points to make it continue. So in this sense, if you try to develop analytic theory over non-Archimedean metric space, you think some lack of points. So the second problem is about point. So the problem number 1 is closely related to the analytic continuation problem, ACP, and the second problem is related to the functoriality problem, which is mainly the problem about points, as we will see later. So these 2 problems actually will cause very serious inconsistency between point sets and notional functions in any rudimentary attempt of non-Archimedean geometry. So let us see this. So hence, one can say the history of non-Archimedean analysis or non-Archimedean function theory is a struggle for solution to ACP, and at the same time, the correct notion of points, the functoriality problem, so to speak. And it has gradually been recognized by experts that these 2 problems are closely related with each other. Okay, so this is the introduction. Now comes the main part of my talk. It's about rigid geometry. Okay, so what is rigid geometry? So rigid geometry has been founded by John Tate. Well, the formal year is 1961. There was a seminar at Harvard University named Rigid Geometry, Rigid Analytic Spaces. And afterwards, this lecture note has circulated without Tate's permission, and actually has been published from Invenciones without his permission. So this is also one unique aspect of the history. Okay, and so here is a Tate's approach to analytic continuation problem. So we have a very fatal problem. So how did Tate solve it? So classically, we start from function theory from the beginning, and having this, we go to the notion of analytic spaces by patching local patches. So first we do local theory and then global theory. So this is the normal way of doing. But here, Tate actually reversed the ordering. So he, from the beginning, he actually established a global theory of analytic spaces from the first place. And he seems to say, this implies that there is a this is a solution of ACP, because there is global theory at one hand. Okay, so in this sense, somehow he successfully ignored that there was such problem. So here lies the ingenuity of his method. He started from the global theory. But now we ask, so how was it possible? I mean, without any knowledge about local theory, how it was possible for him to construct a global theory of analytic spaces? The answer is he constructed the spaces via spectrum of Banach rings. So he uses the spectral geometry, like our algebraic geometry, to construct a space from the beginning. Of course, in the meaning of the meaning of the spectrum lies another problem. So he has to choose his correct spectrum as a starting point, which is closely related to the functoriality problem we are going to encounter with later. And secondly, he patches these spectrum by Grothendieck topology, a kind of algebraic topology that rigidifies the metric topology, that naturally rigidifies the metric topology. I mean, as I have told you, the metric topology is too fine, so he has to rigidify it, and he did it by introducing some fancy topological argument involving Grothendieck topology. This is what he did. In this sense, rigid geometry rather resembles algebraic topology, not complex analytic geometry. So rigid geometry, which is a non-archimedean analytic geometry, so it started, I mean, the motivation, of course, started as an analog of complex analytic geometry. But in the end, it turned out something not so similar, not very similar, to analytic geometry over complex numbers. But it is more similar to algebraic geometry in this sense. Because I mean, it starts from the spectral geometry. Okay, so here is his motivation. He started his argument of rigid geometry by what is called Tate elliptic curves. So he started from this elliptic curve defined by this particular cubic equation. This is an elliptic curve defined over complex numbers. I mean, not over non-Archimedean field. So this is a usual complex analytic situation. Then this elliptic curve has partial uniformization from C star, C cross, to the complex analytification of the elliptic curve, which realize E as C star divided by the infinite group generated by some particular element Q. Okay, and by this uniformization, the functions x and y can be written in terms of the coordinate of C star, coordinate w of C star. So x as a function of w, and y as a function of w can be written this way. It's a finite, infinite series. And B2 and B3 can be written in terms of this. Okay, so this is a classical known formula. It is, even known in 19th century in the theory of elliptic functions, for example. And then, so we consider this the same formula over CP. So CP is a kind of a complex analog of complex number field in periodic situation. It is the completion of the algebraic closure of QP. QP is the periodic field. Okay, so XW and YW can be transformed into this by just easy transformation of the formula, and then you will find. If you look at this rational terms on the right-hand side, you will find that this function converges uniformly on the domain defined by these inequalities, looking like this. So it is a subset of annulus with some hole missing. Okay, so he said that this function has a certain meaning, or also on the non-Archimedean.
What is the norm you're using there?
The non-Archimedean norm on QP. Yeah, the periodic norm. The periodic norm can extend to CP, naturally. Thank you very much for the question. Okay, so then he observed that x and y can be seen as a meromorphic function on that domain, and also can be, if you cover k star by that kind of domain, you will find that this is meromorphic function on whole k star. K is a CP, K is CP. And moreover, one has the surjective map from the closed point. Closed point means the set of maximal ideals in a fine spectrum. I'm talking about algebraic variety GMK and taking a closed point, okay, to the closed point of elliptic curve. So and he said he proved that this map by x and y is a surjective map on the set of closed points. So then he concluded that there should be an analytic geometry defined over K such that for a variety x over K, one has the analytification, so to speak, xn over K, such that the points of xn should be equal to the set of all closed points, like here. Okay, because he successfully recovered the uniformization in terms of closed points. That was a pretty good reason for him to choose closed points as a point of the analytic spaces. Okay, secondly, the map P should be an underlying map of some sort of analytic uniformization from GMKN to EN. So there should be an analytic structure on it so that everything can be realized as a picture in analytic geometry. This was his first sort of aim or motivation to develop his theory. So then maybe I think he encountered with the following idea. Maybe he thought, what should be the building block of the spaces in the new analytic geometry? So let me, for example, list up some basic spaces in geometries. For example, in algebraic geometry, one of the most basic spaces is a fine line, for example. And a fine line is a spectral space. It is a spec of polynomial ring over a field. Okay. If I look at the complex analytic geometry, certainly unit disk or unit polydisk are basic spaces, so to speak. So the unit disk is a set of all complex numbers with the norm less than 1. So this kind of thing should be regarded as the most basic one, and the most of the spaces should be realized as the gluing of this basic building block. And how about non-Archimedean geometry, so rigid geometry? So he has chosen closed unit disk like this. So D1K is a set of element in K with the norm Z at most 1. So can be equal to 1. So it's closed, but of course, as I said before, this is all at the same time, this is open. in the non-Archimedean metric space topology. So why did he that? Because by choosing, okay, so it is open, but by choosing this, then he concluded that the functional algebra, which you can naturally put on this space, are Banach algebra. So if you do not allow this to be equal, then the functional algebra is not Banach. But if it contains equal, then the functional algebra can be Banach. So the functional algebra is a little more easier to handle. So this means that he has chosen rigid geometry to be a spectral geometry of Banach algebras from the beginning. Okay, so then it is quite natural, I think, for him to come up with this algebra, which is nowadays called Tate algebra. So K double-angled bracket X, which is the set of all formal power series like this, with the coefficients lying K with a condition that the norm of an goes to 0 when n goes to infinity. So this is actually an algebra. For example, this is closed under addition because of the non-Archimedean nature of the norm. You can show. So this is a K algebra, actually. And there is a theorem. The power series in K double-angled bracket X are precisely the ones that converge uniformly on D1K and the map from D1K to the maximal spectrum, so the set of all maximal ideals of this algebra. From A to X minus A, the ideal generated by X minus A is actually injective, which is projective if K is algebraically closed. So this is, so to speak, the rigid analytic analog of the classical Nullstern Satz in algebraic geometry. So I think this theorem, even more convinced him that the choice of, his choice of points as the set of closed points is a correct choice for the points of the analytic space. Okay, so then, well, maybe I don't know. He has considered like this, but if, for example, somebody comes into this story and try to think about what is the correct spectrum, starting from Tate algebra, then maybe the first attempt will be the following one. So one might define D1K as an analytic space by the triple, the underlying topological space, SPM, the maximal spectrum with the maximal spectrum of the Tate algebra with the metric topology, metric coming from the norm of K. So namely it is a non-Archimedean norm, together with some presshift O, where O with value open subset U, the uniform convergence completion of the set of all rational functions with no pole on U. So I think this definition of O bracket U is a kind of a very natural one, according to the classically known theorem, the Runge's theorem in complex analytic function theory. So, this is a kind of a sort of honest analog, honest applying the theory of Runge to this situation. So this should be, the analytic function over U should be a uniform limit of rational functions with no pole on U. So this looks very natural, and this looks quite correct sort of candidate for the disk as a first building block of rigid geometry, the analytic geometry over a non-Archimedean field K. But actually there's a problem. The problem, which is mainly due to the two problems that I have mentioned, ACP and FP, is that this presshift O is far from being a sheaf. This is really, really not a sheaf. So as I told you, there are too many coverings. And having too many covering causes that the sheaf condition to be very, very strong. That means that most of the presheaf cannot be a sheaf. And here is a definite. Here's an example. So very, very natural looking sheaf, but this is not a sheaf in this metric topology. So this metric topology should be modified in order for this thing to be a sheaf. Namely, we have to rigidify in some way the topology. So this topology is certainly a nuisance, so to speak. So we have to rigidify this. So Tate actually remedied this by rigidifying the topology by using Grothendieck topology machinery. So I am now going to explain this step by step. So the sketch of Tate, Renault's idea. So now Renault also comes into the story. So here's the idea. So let V be a valuation ring of K, and we at the same time we consider the rigid space, but also we parallelly consider the formal model over V at the same time. So this is one of the most important sort of idea of them. Okay, so there is a reduction map from the maximal spectrum of Tate algebra to spec of lowercase k bracket x, where lowercase k is a residue field of V, residue field of K. Okay, so this reduction map, which is denoted by RAD, red, maps any maximal ideal of the Tate algebra to this prime ideal, M intersection with the V double bracket X modulo pi times V double bracket X. So this gives you a prime ideal in this actually the polynomial ring. So the idea is that if you take mod pi reduction, pi is is one of the uniformizer of the valuation ring V. Okay, so then if you mod out Vx by pi, then you get the polynomial ring over the residue field rather than the power series ring, because all coefficient but finitely many divisible by pi because of the convergence condition. So by taking mod pi reduction, you have polynomial actually, and you can then take the usual spec in algebraic geometry. Okay, so this is the reduction map. So here is a easy graph with the reduction map, not of the Tate algebra situation, but the projective line situation. So for the projective line, it is quite easy to understand what reduction map should look like. So the reduction map from the k-valued point of P1, because P1 is projective, it is same as the v-valued point of P1. So every point can be written as a pair of of elements in V, A, B, and this goes to the A bar and B bar, where A bar denotes A mod pi. Okay, so this is really a reduction map, modulo pi reduction sort of morphism. So having this, you observe the following. So if you look at this P1 version of the reduction map, then here is a description of this reduction map. So if you take the pre-image of a point, for example, the origin, the pre-image of the origin is an open disk in P1K of radius 1. So that means if you take the pre-image of the complement of the closed point, the origin, the pre-image is the closed disk centered at the infinity of radius 1, so to speak. So it's a closed disk. So this means that the pre-image of a point is open disk, and the pre-image of Zariski open subset is something looking like a closed unit disk. Okay, so this already gives you a sort of a guideline, what kind of open set you should consider. So one should treat the pullback of Zariski open subsets by the reduction map as admissible open subset rather than points. So this means that from the beginning, Tate requires reduction map to be continuous, okay, with respect to the Zariski topology on the reduction. So, but then we ask ourselves, so if the open set are just the preimage of the Zariski open subset, then we only have as many open subsets as Zariski topology. But we would like to develop analytics geometry, right? So we should have more open subsets. So how can we get more open subsets like this? Here is a trick. So there is a reduction map from P1x, P1k to P1 lowercase k, but you can, for example, blow up here at the origin to change the model and take the preimage of 0. Then the preimage is a slightly small open subset with the radius slightly smaller than 1. That means that if you take the complement of this, you have slightly bigger or closed open subset. So in this way, you can come up with more open subsets. So you take the preimage of Zariski open subset, and at the same time, you change models. And this gives you more and more open subset. And this is the first sort of idea, to get enough open subset to develop the analysis. So now comes the definition of dk, d1k as a spectrum. So points are the maximal ideas in k, double bracket x, as before. And now comes the Grothendieck topology. So admissible open subsets is equal to the pullback of reduction map of Zariski open subsets of a model, where model can vary. Okay? And admissible open coverings, I mean, the Grothendieck topology should be defined both by open subset and also open coverings. So the admissible open coverings should be defined to be the preimage by the reduction map of Zariski open coverings of a model, where model can be changed. Okay? And function algebra, just as before. And here the model means formal admissible blow-up, like we did in the previous slide, of the formal scheme SPF V double bracket X. And now comes the theorem. So this is a very, very, how to say, turning point theorem in the development of rigid geometry. So very, very important theorem, so to speak. Tate acyclicity. So the function algebra, defined like this, over the Grothendieck topology defined like this, is actually a sheaf. So now we have the final solution for the correct building block for the rigid geometry. So here's a small remark I'd like to add. The Grothendieck topology, which I have introduced here, actually is weaker than the weak topology. So there is two notions in Tate's definition of topology. So he has strong topology and weak topology. And our topology introduced here is even weaker than weak topology, which turns out a posteriori to be equivalent due to another very famous theorem, Garrett and Grauwald theorem. So it is, after all, equivalent, but it is not actually not the one which John Tate has considered for the first place. Secondly, Tate's original definition of topology is given by the notion of affinoid subdomains, which is a little more complicated, a little more sophisticated, which are defined actually by means of universal mapping properties of rings. The weak topology and the strong topologies are also equivalent. So all these topologies turn out to be equivalent after all, in the sense that they give the equivalent topocies. So equivalent means that, of course, weak topology is weaker than the strong topology. But they are equivalent in the sense that they give the same theory of topocies, same theory of sheaves. So in this way, they are equivalent. Okay, so now comes the, for example, the definition. Do I have a time? Okay, fine line, for example. So a fine line can be constructed by patching. So as a point set, a fine line should be consisting of the maximal point, the closed point of the polynomial algebra, as usual. And we already know that there's an injection, U0, which is the so to speak, the closed unit disk, to the affine line. This is injection. And you can stretch this, you can scale this U0 by multiplying some value. So UN to be, for example, the SPM of the Tate algebra where the variable is replaced by C, nth power of C times T. So that this realize some bigger radius ball in X. And then you find that X is covered by all UNs by stretching larger and larger balls, which gives the analytic structure of X, which is the definition of the analytic structure of a fine line by John Tate. And there's another analytic covering. Of course, the analytic structure may have several different analytic coverings. Another one is this, so Wn and U0, you start from U0. This is a closed unit disk of radius 1. And Wn are annuli, okay? So with so defined by this inequality of norms. and these annuli are ordered. Yeah, like you can just imagine. So now a small remark, the circumference, this is a very, it may seem to be a very thin set. It is very thin in Archimedean situation, but they are actually open subset in this context. So you don't have to worry about it. This is a gluing of open subset along open subset. Okay, so this is the algebra of the annuli. This can be written as this by using a new variable. So it has a formal model like this, where K is replaced by the valuation ring V. And so the reduction, so reduction mod pi here amounts to the same as C is put to be 0, gives you this. So this is a normal crossing of two affine lines. So the reduction is two affine line, so which we have already encountered in some slides in the previous slides. Okay, so and we have also now we can do the Tate uniformization. We started from. That was the motivation for Tate to develop his analytic geometry. So Wn gives analytic covering of the GMK, which is the affine line deprived of the origin, where n it runs over any integer. So you do not start from unit disk. You cover this affine line minus 0 by infinitely many annuli. Okay. Then the reduction of GMK with respect to this analytic covering is the infinite chain of P1s. And if you, for example, take Q to be some non-zero element in K where the norm of Q is less than 1, and if you consider the action Z on the multiplicative group analytification by T to the Q times T, then if Q is, for example, equal to some power of C, then this analytic covering actually is compatible with this action. And that means that the Q maps Wn isomorphically to Wn minus K. So what's happening is like here. So you have this concentric annuli, which covers your GM, and Q acts on it by sliding, K times the annulize. And by modding out by this action, you have something like this. Of course, you should not believe this picture, but you will have something like this, which looks like an elliptic curve in this analytic sort of geometry. And in terms of the reduction, you have something like this. You have a reduction. In the reduction, you have a chain of P1s, and action by Q slides the component K times by K. And the quotient is a cycle consisting of K P1s. like in the classical reduction of elliptic curves, classical semi-stable reduction of elliptic curves. So this somehow completes the description of Tate elliptic curve, and also the so to speak the description of a basic description of rigid geometry. So let me finally list up some of the historical events in rigid geometry. So John Tate's paper came out in 1971 without his permission in Invenciones Mathematica. And there was a historical paper, Gerritsen and Grauert, which I have mentioned before. And also Kiel wrote a very famous paper which proves the analog of theorem A and theorem B by Cartan in rigid geometry. And finally, in 1972, Michel Renaud came into the scene and has proved a very famous and very impressive theorem which relates rigid geometry on one hand and formal geometry in algebraic geometry on the other hand. He said that rigid geometry is a formal geometry modeled by some sort of set of morphisms which are called admissible blowing ups. So if you invert all this admissible blowing up, what you get is precisely rigid geometry. So this is a very nice bridge between two different looking geometry, rigid geometry and formal geometry. So this is one of the most sort of breakthrough and epoch-making theorems in the history of rigid geometry. And this somehow is sort of a very, very kind of final state, final completion of the solution for the ACP, analytic continuation problem. But later we will see that this actually do not solve the other problem. So I'm going to point out actually that still rigid geometry is not strong enough to solve all problems. We will see. Okay, but before that, let me talk about some applications of the rigid geometry. So already in old days, there are so many people working out in applications in rigid geometry. So the first application which come up to your mind is about, for example, the analog of the theory of Riemann surfaces in rigid geometry. So how should it look like? So compact analytic curves are all projective. It has been proven, this. So this has been a long time folklore and has been, published by one of my students, former students, Mitsui. And also the notion of compact analytic surfaces in rigid geometry has already worked out by Kenji Ueno, my former supervisor, already in 1997. And he has discovered some non-algebraic and new analytic surfaces. And final remark in this slide, there is a full-fledged theory of Gaga, geometry algebraic, geometry analytic, which bridges the geometry, algebraic geometry and analytic geometry, which also was in complex analytic situation, which you can find, for example, in SGA first. But you also have a fully analogous theory of Gaga in rigid geometry. Okay. So I have mentioned about the Tate uniformization of elliptic curves, but this uniformization has been vastly generalized by David Mumford in 1970s. So there is a theory of Mumford curves. So gamma is a discrete free of finite rank subgroup in PGL to K, and you take the complement of limit points of the gamma, which is like, for example, if in complex analytic situation, you have a modular quotient, right? Modular curves. In that case, you take gamma to be the Fuchsian group, and in that situation, the set of limit points is the real line. So you subtract real line from the projective line, over C gives you 2 copies of upper half plane. The other one is lower half plane. So, so this omega gamma is a sort of analog of this one. Okay, so you can take the quotient of omega gamma by gamma. Then this can actually be algebraized to a smooth proper curve over K. And you can also talk about the semi-stable reduction of this, because I mean rigid geometry, the space in rigid geometry comes together with the formal model always. So so it has a formal model, and you can then talk about the model pi reduction of this formal model. This gives you a graph associated to this dual graph of the. This is isomorphic to the graph obtained by the tree associated to graphs, gamma, so to speak, divided by gamma. So it can be combinatorially completely described. So it's a very, very beautiful theory. And there's also a theory, analog of modular curve in positive characteristic rigid geometry. So non-Archimedean analog of modular curves in positive characteristic. There is also such a theory. And also there is a higher dimensional generalization which has been worked out by Kurihara and Mustafin and many others. First successful application of this higher dimensional situation is the construction of the so-called fake projective plane. So this is a very nice story, actually. It's a complex surface, smooth, compact, and has the same Betti number as the projective plane, but it's not isomorphic to projective plane. So this is the definition of fake projective plane. And this, the first construction of fake projective plane came out from David Mumford by using non-Archimedean uniformization. So interestingly, so this is a complex surface, but in order to construct this, he did by applying rigid geometry. So anyway, so this is a non-Archimedean. So there are more applications. There are in fact huge diversities of applications of rigid geometry to algebraic and arithmetic geometry problems. So here are only a few of them. So periodic uniformization of Shimura varieties. I mean, periodic uniformization can be applied to a certain kind of uniformization of a certain PEL type Shimura varieties. And there is also a very impressive application to Bianca's conjecture by Renault in 1994. And modularity of Galois representations, and also there are related topics about, for example, rigid cohomology or periodic differential equations, and more and more. And these are already, I mean, quite famous and very, very well-researched sort of areas and research fields. So now comes, I would like to also mention something, some other kind of non-Archimedean geometry, which contains, for example, Berkovich approach, which is somehow related to rigid geometry. And of course, in many, many important cases, Berkovich geometry is just equivalent to rigid geometry. But of course, I mean, there are many, many different aspects. So, I'm sorry, so this is something else. I mean, why, what happened? Okay, so Berkovich geometry, so Berkovich spectrum. So he also starts from a spectral geometry. For Banach algebra, M bracket A, it's a set of all bounded multiplicative seminorms on A. So rather than taking a maximal ideal, he take all seminorms, and this is his idea. Then he come up with more sort of a nicer looking, beautiful space as an I underlying space, in the sense that, so as I have told you, in non-Archimedean geometry, you have a fatal and serious deficiency of points. It is like the set of all rational numbers in the set of real numbers. Okay. What he did in this context can be compared to recovering real points which are not rationals to fill in gaps in order to make it more continuous looking space. So he adds more points in rigid geometry. And in order to do this, he has taken semi-norms. So this was his idea. And so now here I had a picture of projective line in Berkovich geometry. So this is like a tree with the tips, limit points, or are on spheres. So the P1 is like sphere. So, but the Berkovich spaces not only consist of these sphere points, which are type 1 or type 4 points, so to speak, but also he has a point, he has a locus that connects these points to other points. In this way, he somehow recovers the connectivity of the rigid geometric spaces as a space. So it is a tree without ends, nearly equal to the closed points of P1K, which are their points in the sense of Tate. So the Tate points are on the sphere, and all of them, and all the other of them are the Berkovich new points. They are, so to speak, the generic point of closed disks. So here is a picture. So you have this Tate point, the classical point, and centered at this, you have several closed disks, glowing disk, the stretch of the closed disk, and corresponding to each of these disks, you have the points inner sphere, the sphere inside the sphere, and that constitutes the tree-like structure of the Berkovich space. Okay, so there's another theory, which is so to speak birational approach, which is an ongoing joint work with Kazuhiro Fujiwara and myself. This has already been started in the year 2003, so we have actually worked for 19 years. But the first book actually came out in 2018 from European Math Society. The title is Foundations of Rigid Geometry 1, and this contains 3 chapters, Chapter 0, Chapter 1, Chapter 2. And Chapter 2 is about the rigid geometry. And we are now preparing the second volume. Hopefully, it will come out in a few years or several years. So our basic policy is that the rigid geometry is the birational geometry of formal schemes. So the spaces are, so to speak, the Zariski-Riemann spaces, which is the projective limit of all admissible blowing ups of formal models. And this gives much more points than the Berkovich points. So to speak, Berkovich points has 4 types of points, and we add more points, more type of points, which somehow complete the set of points. And most importantly, these points are necessary and sufficient. We found that for the perfect consistency between spaces and functions. So this actually finally solves the functoriality problem. What are the correct notional points for the rigid geometry? So in the sense that, I mean, taking this set, this topological space as underlying topological space, you can recover the correct topos of the analytic space. So in this sense, we can say this in this sense is necessary and sufficient. And this is also similar to the theory of Hilbert's adic space. Okay, so my time is already running out. So so this is a relationship between the Zariski-Riemann space and Berkovich space. And so the contents here is that there is a separated quotient from Zariski-Riemann space to some Hausdorff-looking good topological space. And so this is essentially the Berkovich space, so which relates our space to the Berkovich space. And our space can be realized as a fibered space of a Berkovich space. So the picture is looking like this. So our space is this, and project to the Berkovich space and take the skeleton. You have a fibration of your, for example, elliptic curve over S1. Okay, so then Quite recently, I have worked out, in the joint project with the Garo Binyamini in Weizmann Institute, rigid geometry over Z double bracket T. So this is not a valuation field or the valuation ring, but it's a complete ring. So still we can develop some sort of rigid geometry. And we can actually apply this to prove a uniform version of Piller-Wilkie type inequality. It has been already appeared in archive with this number. Okay, so here's our theorem. We have this inequality to count a rational point in the transcendental part of some analytic space. Has been upper bounded by some constant times some height bound. This sort of thing. Okay, so finally, I would like to mention that there are 4 different approaches to rigid geometry nowadays. One is the classical rigid analytic geometry by Tate and Renault. Another one is adic spaces by Huber, Roland Huber. And our approach, the Zariski-Lehman space approach by Fujiwara and myself. And the final one is Berkovich spaces by Berkovich. And at least over DVR or some more, a little more general situation, very important general situation. The first 3 are the same theory, but B is slightly different because the underlying topological space is different. The underlying topoi are something different. There is a morphism from the topological space or topoi of the first 3 theory to the topos of the Berkovich space, which is a quotient as a topological space. So this somehow explains the relationship of between these 4 theories. So I'm sorry, so I extended my time. So thank you very much for your attention.
Thank you very much. Are there any questions? Sure.
It's nothing particularly important, but I'm just curious, why did Tate not give his permission, and why was it without his permission? How did that happen?
Well, if I had a chance to ask that question to himself, to John Tate himself, I would have done that, but I actually have never met him, so. Okay. And I actually, I'm also curious. I don't know why. Sorry.
Any other questions? So you mentioned something about the classification of surface, like an elliptic surface. I think that in a complex geometry there are many elliptic surface, which is not algebraic. Are there anything like that in?
Yes. That's what I have meant here. Actually, Kenji Ueno has given a sort of classification, and in that he also has pointed out that some of the analytic surfaces which can be constructed, for example, by means of an analytic method like uniformization, are actually not algebraic. Like, for example, Hopf surfaces can also be in this context. But he also mentioned in this paper that, there are 2 kinds of Hopf surfaces. One is the algebraic dimension 0 and algebraic dimension 1. And there is no algebraic dimension 0 Hopf surface in this context, he said. He actually proved it. So there are a slight difference between complex analytic classification and rigid analytic classification. In this sense. And also I have mentioned here that there is also a logarithmic transformation sort of method in order to cook up a new surface from a given surface.
So you also mentioned that something like a group action on a complex plane and some singularity kind of Tahimura theory. So that kind of classical, some deep theory of Tahimura theory is kind of generalized to this kind
yes,
of thing.
actually there is a Tahimura theory that that parameterizes manifold curves, because manifold curves can be realized as a uniformization. So for example, you can develop the analog of the classical Teichmüller theory by classifying all possible gamma up to conjugation in PGL2K. This gives you a Teichmüller space parameterizing manifold curves. There is such a theory.
Like quasi-Fuchsian group?
Well, Well, I guess so. But so far, I do not know. I mean, anybody. I mean, I don't know whether anybody had done such a work or not. I mean, you mean sort of degeneration of gamma, right? I think this is quite interesting. But I don't think there is no such theory so far, I guess.
Maybe people in dynamical system do not know so much about this.
The dynamical system of yes, yeah, but of course, I mean there is in different contexts, there is a good theory about dynamical system for example, in Berkovich space. Using Berkovich spaces, which is quite important from arithmetic point of view.
Any more questions?
So you have a beautiful vibration picture from the elliptic curve down to Berkovich space, which is what happens if you replace the elliptic curve by a K-free surface?
So that kind of vibration structure depends on your choice of the formal model. So for example, if you're K3 surface, so I'm not so knowledgeable about the rigid analytic topology of K3 surfaces, but I think the K3 surface may be just simply connected over non-Archimedean field, or have some little more non-trivial topology. So in any case, if it has, for example, the non-trivial reduction, like type 3 reduction or type 2 reduction, and so on and so on. Then corresponding to this, you have a similar vibration, like for example type 3 reduction. If your K3 surface has the type 3 reduction, then taking that formal model to construct the skeleton on the Berkovich avatar, then there is a vibration from your K3 surface, the Zariski-Riemann avatar of the K3 surface to a sphere, for example.
Type 3 reduction is Kulikov type 3?
Sorry?
Is that Kulikov type 3 degeneration?
Yes, yes. What I mean by it's algebraic degeneration, yes.
So you do expect the base to be a sphere?
Yeah, in type 3 case, right. Yeah.
And presumably that's the connection you were talking about.
Yeah. Yes.
Yes. Yeah, now comes into such more deeper. Yeah, so maybe there are many things we have to discuss.
More questions? So thank you very much, speaker.
Thank you very much.